Hello, everybody. This is my lecture for week 11, session 1. So, in today we will go over chapter 3 and 4, piping systems. Sorry, I'm sorry. And this is actually short review of fluid mechanics course. So, in fluid mechanics, you learned the Bernoulli equation. Actually, you saw the different forms of energy equation in fluid mechanics, in heat transfer, and thermodynamics. If we assume that heat transfer there is actually negligible, and also the system is work under the steady state condition, and also the viscous forces are negligible. So with these three conditions, negligible heat transfer rate or adiabatic process, a steady state condition, and also negligible viscous forces, we can simplify the energy balance equation, and then we can just derive the Bernoulli equation. So in Bernoulli equation, actually you can write this energy balance for 2 points. And then V is the velocity, Y is the elevation, P is the pressure, rho is density, HA is head added to the system, HR is head removed from the system. Normally, if you have a pump, you have HA. If there is a turbine in the system, you have HR, and HL is the actually losses. So you can write this equation for 2 points. Keep in your mind that each term in this equation has the actual length unit, either meter or feet. And so in this equation, what you need to do, you need to calculate the losses, HL. And then if you remember, the total losses is a combination of major losses and minor losses. Major losses is due to the actually pipe lengths, and HL normally is actually due to the bends, valves, elbows, and these things, connections, expansion, contraction, and actually this element in piping system. So major losses normally can be determined by using this equation. F is the friction factor, L is the pipe length, D is diameter, V is velocity. And then minor losses can be determined from this equation. KL is a constant. You can normally find the KL from the reference table. V is the velocity. So to use the Bernoulli equation, you need to calculate the total losses. To calculate the total losses, you need to find F, friction factor, and also this KL. Keep in your mind that in this equation, if you have non-circular conduits, then you need to use the hydraulic diameter. We already discussed the hydraulic and equivalent diameter in previous sections. So hydraulic diameter is 4 times cross-sectional area of flow over weighted perimeter. Okay, so what we need to do, we need to find F and KL actually to use the Bernoulli equation. To find the friction factor, actually friction factor depends on the flow region. For the laminar flow, F is 64 over Reynolds number. If you remember, for internal flow, the critical Reynolds number is actually 2,100, sorry, 2,200, or in some textbooks, such as German textbook, is actually 2,100. So in some textbook it's 22, and some other 21, 100. So for the case, if you have a turbulent flow, you can use Chen equation, Churchill equation to find the friction factor. So what you need to do, actually, you need to find, you need to have the Reynolds number and also epsilon over D. So epsilon is the roughness, and epsilon over D is the relative roughness. So in Churchill equation, what you need to do, you need to find the C and B, and both C and B depends on the actually Reynolds number and relative roughness. In addition to this two correlation, you can use other correlation as well. For example, you can use Hawaiian equation, which is valid for this Reynolds criteria, and some other equation. If you search, you can find several different equations to find the friction factor. So you can either use this correlation, or you can use the Moody's diagram as well to find the actually friction factor. So for the roughness, you can use the reference tables to find the roughness for different, materials. For example, you can use table 3.1 from the Jonas textbook. You can find the roughness based, in feet or millimeter for different materials. Also, you can use the Moody's diagram to find the friction factor. So if you are actually solving a problem, actually needs, let's say, iteration method to solve the problem, then it's a good idea if you use, these correlations to find the friction factor. Otherwise, if you have a straightforward uh, problem and you just need to find a friction factor, you can either use those correlation or the friction the Moody's diagram. For the Moody's diagram, you need to have the Reynolds number. For example, if you have Reynolds number, let's say 10 to 7, and the relative roughness of 0.001, then you can simply find the friction factor. Uh, this line is for the smooth actually pipe with epsilon over d equals to 0, and this line is for the laminar flow. Okay. So for the minor losses, we discussed that minor losses, just a quick reminder, is due to the valves, bending, elbows, and these things. So we have actually two methods to determine minor head losses. So the first one, we already discussed the first one, HL equals to K, coefficient or loss coefficient times velocity square over 2G. What you need to do, you need to find K. Keep in your mind that the HL, the head loss, equals to the delta P over rho G. So you can find K from the reference table. For example, you can use table 3.2 from the Jonas textbook to find, the K value for different conditions. For example, for 90-degree elbow, you have two options for the threaded one, for the flange welded, or good bell and square. So for these two different cases, you can find K for different options. And also you have some other options. For example, for let's say here for contraction, for expansion, you have different equations to find the actually K. This part is for different valves, so depending on the valve types, and also if this is a threaded one or flange one, you have different equations to find the K value. This is the first actually method to find the minor losses in this textbook. In this course, normally we use the first one. In some textbook, in some other actually textbook, or some other courses, you may use this method, the equivalent lengths, to find the minor losses. So you can write the HL minor equals to the F L equivalent V squared over D2G. In this actual equation, what you need to do, you need to find the L equivalent. And the L equivalent is the length of pipe that produce a head loss equivalent to the head loss in the particular fitting. So what you need to do, you need to find actually L equivalent and friction factor. So if you want to use this method to find the minor losses, first you need to find the L equivalent from the reference tables for different actually fitting valves and these things, and then you use the Moody's diagram to determine the friction factor, and then you can find the H L. So what's the relationship between K and L equivalent? This is equate this actually the K value for K and also L equivalent for different fittings. So yeah, if you have the based on the fitting, you can just pick the value for the L equivalent over diameter, and then you can find the L equivalent. So what's the relationship between K and L equivalent? If you write the HL minor losses for K Based on this format, kv squared over 2g, and also fl equivalent v squared d over 2g, and then you compare these two equations, we can show that the k equals to the fl equivalent over d. So this is the summary. This is the, actually two different equations to find the major losses and minor losses. And keep in your mind that if you want to calculate the overall losses, if you have several components in series, so you can write the total head loss equals the sigma HL major plus HL minor. Keep in your mind that this equation is valid for series component. What about the parallel component? We'll discuss it hopefully, I think, next in actually two lecture about the parallel components. And yeah, if you have the circular conduct, then you need to find the d hydraulic. I mean, you need to substitute hydraulic in all these equations. So here there is a just simple example for the application of how to calculate the major and minor losses. So we have this system, and if you look at this example, you see that we have several components in series. So we have some elbows, major losses, minor losses. Also we have valves, there is a filter, so there's expansion here, contraction here. So you are asked to calculate the total losses. So the total losses is sigma HL major plus sigma HL minor. So for the HL major, depends on the actual pipe length. We have the pipe length is 200 feet. And then for the HL minor, what you need to do, you need to actually find K value for all these component. Actually, we have the K value, correct, for each component. So yeah, you can write the HL total is HL major plus sigma KLV squared over 2G. So what you need to do, you need to find the KL for these different elements, and then find the total KL. So to calculate the major loss, you need to find the F friction factor. To find the friction factor, you need to have the Reynolds number and relative roughness. Relative roughness is available here. You need to find the Reynolds number. Reynolds number, you need to have the diameter. So the diameter is known, and also you need to have velocity and viscosity. So we have velocity and viscosity here. So we can simply find the Reynolds number, which is V times over mu. So you can find the Reynolds number, you have the relative roughness, and then from the Moody's diagram, or by using one of those, correlation, you can find the the friction factor. So based on this, Moody's chart, the friction factor is something around 0.039. So you have the friction factor. L is known, diameter is known, velocity is known, so you can simply find the HL major, and then you have the KL for elbow. There's 1, 2, 3, 4, 5 elbows, one valve, KL, and expansion and also contraction here. So if you add all this, KL, you can find the sigma KL. So this is the solution, for this problem. Please go over this problem. This is actually a short review for the fluid mechanics. Next lecture, I will go over the single pipe, how to solve the problem includes single pipe. We will go over one method that you already learned in fluid mechanics, and then we will learn two new methods to solve, actually to analyze the system includes a single pipe. Thank you very much, and have a great day.